and some sound. Okay, let's check the sound first. Do we broadcast any sound? Does it sound okay? Great. Okay, so I've upgraded fairly recently to Ubuntu 18.04, and it added like 7 minutes or something to the startup time or reboot time of my computer. But today's lecture is unit testing and test-driven development. So it's sort of the base for the first assignment and the second half of the first assignment. Hopefully you've already started and perhaps also completed the first assignment, the first part of the first assignment. If you have not, the deadline is November 16th, so you need to start in time. And yeah, there is tutoring during the week, so please use that in order to get help if you need help. Okay, today's lecture is going to be, we're going to start with a bit of repetition, and then we're going to talk about unit testing, and then a bit about test automation and XUnit frameworks. I'm going to showcase some examples from JUnit. I'm going to talk about code that is harder to test than other code, and also the sort of solution for that, which is mocking, and a very short slide of quality of test suites, because that is the content of another lecture. And then finally, we're going to do some talking about agile testing. Hopefully you've seen the videos I asked you to watch before this lecture. And finally, some test-driven development. Test-driven development demo things. Okay, so first, repetition. Testing does check conformance to requirements. We conduct testing in order to know if the implementation we have fulfills the requirements we have. So we want to conduct testing in order to do that. We understood or sort of learned that in order to do good as a tester, we must understand the requirements. And when we're testing our software, we get a deeper understanding of our requirements also, because we try to put ourselves in the shoes of the customer or the end user and test the system as the end user with the amount of data required to test the system and such things. And then we understand how the software is supposed to work. We understand that the slider should not be on top of numbers. We understand that, such things. It also helps us to build confidence in the software, in the code, so that we dare to sell our product and when we dare to release our product to customers. And it's also our customers or the end users' confidence in using this product that is on stake. And we've learned that it can be pretty expensive. And I'm going to talk about that on the next slide. We do testing and then we uncover problems. Errors made when implementing this software, or errors made when we thought up the requirements for this product. And these errors result in faults, which are defects and also called bugs. The testing is a base for some kind of decision making. Perhaps we can release this product, or perhaps we can say that this product is fairly good tested enough, or we should conduct more testing, or we need to fix these bugs. Testing does not prove a program is correct. That was verification, right? And something that should have been in the first lecture. And if I click this link, we can see a lot of different pictures sort of showing increasing diagrams. And this is also a reason to do testing and do it early and do it during the development of the project. What we see here is the relative cost of fixing defects depending on which stage our project is in. Most of these images are like waterfall process images. So first there are requirement engineering, and then we analyze all the requirements, and then we design something, and then we test it, and then we put it in production. And sort of these images sort of shows that if we find a defect or a problem or something that we thought was wrong really early, the cost is almost zero, compared to finding a bug or a defect really late. Then the cost is really high to fix that problem. And I mean, in the first requirement stage of a waterfall model, then we're in the idea mode. So we're still thinking about what requirements are we going to have, and if we fix a problem there really early, it's negligible cost. And so, but I mean, the sort of environment that hopefully you end up in is a bit more agile. So perhaps we don't have these waterfall processes. We have some agile process where we think about doing implementation and doing testing and doing perhaps also releases to the end user during the cycle or development cycles, and we have different phases, but this still applies. And some of what I mean with this is that fixing defects late is costlier than fixing them early. And some of the cases I showcased during the last lecture was that I found defects late, and it affected me as a customer or end user of one product, and also as a developer, right? It's feeling ashamed of your product is never a good thing. Okay, so that was sort of the repetition and something that perhaps should have been during the last lecture. So during this next part of this lecture, we're going to talk about unit testing. And so unit testing is testing of a unit. A unit can be a class, a method, or a component. What I, damaged as I am from conducting unit testing with JUnit, I almost always think of first testing a method. So unit test for me is mostly a test of a method, but this method could be, it can really be testing more of the system than just that single method. I'm writing in isolation here also. We want to test one thing and not the other things with one test. And the reason for that is that we want to find out, is the problem here? We want to get a direction to a possible defect, or a clue to what is the source of the error. And you've probably done a lot of testing already. I mean, manual testing is still testing, and unit testing can be manually done. I'm going to showcase an example of that. We can easily automate, perhaps by hand, perhaps by using if statements, also testing. We can use random testing, and I'm also going to showcase that. And we can use an automation framework, and I'm going to showcase that also. But first, before we start with that, we need to think of what kind of, if I check this one, we should check conformance to requirements, we should get a deeper understanding, we should get this confidence, we should sort of build knowledge of our system. And the way that we do that by conducting testing is that we get something back from doing this test. We get some feedback back, we get some information from the test, and we want that information to be good. And sort of just from the if statement of the test, just from the decision by the oracle if the test succeeds or not. It could be an if statement, right? We get either that things works as specified, or we get that we got something else, or the system crashes when we run the test. The unit crashes, perhaps. And I would argue that all three have value. So if I run my tests and everything works as specified, then I gain confidence, right? If I get something else, then I see, okay, something is wrong. I get a clue that something is wrong. If the system crashes, it could be a good thing. It could be deliberately made to crash, and we want it to crash. With crash here, I mean it could be like an exception thrown that we don't expect in these circumstances. It could be that we do something that is illegal within the language or code that we have, like divide by 0 or something like that. That is not allowed. This depends on the programming language that we use and the sort of way we run these tests, what we count as a crash. We can also design, and I talked a little bit about that during the last lecture, but didn't really dive deep into that. We can also design our program in such a way that we deliberately get crashes if something is wrong. And if you build a system where the output of the system is really important, perhaps you build a compiler for a programming language, then the compiled executable file that we get in there, it's really important that that one is correct. Because some programmer is going to use our compiler to create code and they want to rely on that code. In such a case, when the output is really important, then we would prefer during development that the program crashes and that we find some information from that and can use that information to improve the product and remove these faults. Except from these things, I would say that if we write our tests in a good way, we get more information. Perhaps we could, when we're writing our test, we could like talk to the programmer who reads the test, and we could like give him information on what was tested, why was it tested, what kind of scenario did we have, what kind of input did we provide, and what should have happened instead of what you got. So we could write perhaps a name of the test method, if we're going to use that provides that kind of information. We can also like help when we're writing these tests. We could also like help the future programmer that receives this test report by making sure that a test tests one thing and test one unit, so that this programmer does not need to play Sherlock Holmes in order to find where is the problem in my code. Do you remember the story of the blue screen from the last lecture? The problem was that I didn't know which part of the code the bug was in. And I needed to play Sherlock Holmes in order to find this. And I spent 6 months playing Sherlock Holmes. It's really costly. And what if I could write a test that points me directly to the position of the bug and gives me enough information so that I can understand the situation where the bug was occurring. So the better information we sort of get, the easier it is to fix the problem, to fix the fault. Okay, if things crash it provides input for us as programmers to fix these. If it provides unexpected output, then we get something to build on. Okay, I need to fix this. And if it works as specified, then I get a confirmation that I'm doing something right and that I didn't break things, perhaps. So let's take an example, and this example is pretty simplistic. You remember that a test case, not only a unit test, but a test case has input. It has some kind of system under test. That was the method or the the thing that we want to test. And it also had some expected output. So in this case, we have a method called max. It takes an array. In this case, it takes the array input that has 4 items in it, and it should provide the largest of the items. So given the input 4, 3, 2, 1, the expected output is 4 because that is the max of this array. And then on line 3, actual equals sut.max input. This is where I run the method that I intend to use. And we call that exercising the system under test. We run the code that we intend to test. So if this test fails, I know that the problem should be in this method. When I run when I exercise the system under test, then I get something back. I get an actual output, or the actual behavior of the thing. And this actual can be compared to the expected value. In this case, I just compare them with an if statement, but it could be us as manual testers who look at a colored box on the screen and compare that to whatever we expected that to be. So in this case, we're testing code by this, but it could be some output of the screen, right? If I am the oracle myself, in this case, I've coded the oracle as an if statement. So the if statement checks if the actual is not equal to the expected. If it's not equal, then something is wrong. Then we report the error. And sort of the if statement and the line below is sort of what most unit testing frameworks have asserts for. Everything super clear? So what is... Last lecture we talked about input domain. That was the domain or the collection of all possible input variants we could come up with for a method, right? So what is the input domain size for this method? We have an array of integers. And this is Java. So we need that information also in order to solve this assignment. So think about that. An integer normally in Java is 32 bits. You need to know that. So each item in this array is 32 bits. And then we need to know how many of those items. Because every item in this array, if it were just one integer into this, it would be a 32-bit number that we're looking for, right? 4 billion something. But in this case, it's an array, and we need to know how many items can be in this array in order to solve this assignment. And I just Google it. These are some cases just for, I didn't actually know what's supposed to show up here. But these are some possible input arrays. You can see that 1, 2, 3, 4, and the other one 4, 3, 2, 1, 5, -5, -3. These are different inputs in the input array. But really, the number of combination is super huge. We must take 2 to the power of 32 and multiply that with itself, 2 to the power of 32 minus 5. That is the largest array number according to this Stack Overflow question. So it's super huge. It's really, really hard to test all these. We cannot do exhaustive testing, and that was the word. So verification, if we want to be absolutely sure, if we want to prove that our code works, we need to move to verification with works creating a mathematical model of our code and do that thing, which is not the case for this course. So instead of doing that, we need to select some tests, some smart test cases, and this is called the test selection problem. We need to select some test cases that will have high probability of finding the bug. And I've written a couple of those up there that just from the top of my mind. Okay, let's have an increasing array, let's have a decreasing array, Let's have an array with only negative numbers. Let's have the edge cases around 0, if that can matter. Let's have an empty array in the end. Something like that. Different cases that could be good to find this. We're going to talk about strategies for finding these cases in a later lecture. Right now, we're just, okay, let's test this manually, perhaps. So I've written an implementation. And this is, and just for the fun of it, I have, can you read this? No? Anyone using IntelliJ? I started using IntelliJ last Friday, so increasing the font size of this, I don't know how to do that. Anyone? Does anyone know how to increase the font size in IntelliJ? Control rolling upwards is the usual thing in. Well, let's ignore that for now. This is the method getMax. It takes an array of integers as input. It will throw wrong input exception during some cases. I've created a faulty implementation, and I'm just going to flash that for faulty implementation. You, of course, found all the bugs just by looking at the code. We could do static code analysis. We could do code review of this code, but I'm not really interested in that. I just want to run this code and see if we can find the problem manually. So let's, I've created a small testing application, and we're building the tests. And this testing application outputs a simple user interface for me. It so happens to be console-based. Enter an integer array separated with space. So let's do that. 4, oh, with space, right? 4, 3, 2, 1. The max was 4. So gained some knowledge now. The test case succeeded, if someone wondered, right? The implementation found the largest item of these, and it was 4. 4, 3, 2, 1, and the largest is 4, right? So everything seems to be working. Perhaps we can release this to someone. Does someone somewhere have another test case for me? Negative numbers? So let's just read the numbers aloud and let me, negative? Negative 5. Negative 3. That's enough? The max was negative 5. Oh no, you found a bug. Good work. A small round of applause. Yeah, so now the detective work starts, and we could continue to enter cases. Let's enter just 0. The max was 0. Oh, that seems to work. 1, 2, 3, 4. The max was 3. Oh, that was weird. And we sort of gained a bit of knowledge here. We saw that when we had your fantastic input that first discovered a bug, it was -5 and -3, and it took -5. So it took the second largest item something. So perhaps there's some problem with the last item. I don't know. Let's try that. Let's try that again. Let's have something like 4, 3, 2, 5. Ah, the max was 4. Sort of what I did there was I formed, I cannot pronounce this word, hypothesis. Is that correct pronunciation? So I formed a hypothesis, and then I got some feedback back. So I can use this during manual testing. So let's look at the my math. Oh yeah, you were correct. Something was wrong. I'm actually gonna just fix the problem. Perhaps everyone could close their eyes for a moment. So it was length -1, and then we save that, and then we move to our we need to break this. I'm going to crash it instead. And then rerun this manual testing application. So now I have fixed the problem, perhaps, but I don't know if I fixed all problems. I don't know if I actually fixed the problem that, that we found. So I need to conduct regression testing. Run test cases again in order to build new confidence in the new product, because I've changed the product now. So let's do that again. Let's take 1, 2, 3, 4. The max was 4. Fantastic. 4, 3, 2, 1. Max was 4. -5, -3. Max was -3. Yeah, that is the max. And you heard me almost stumble there, right? Is -5 bigger than -3? And I was sort of thinking of the requirements. And this can be the case also when we work with requirements. In this case, it's math. It's pretty well defined. But in many cases, what is the correct behavior is not that well defined. It could be not that good specified in the specification. It could be also be that we're discovering that the specification is wrong. Okay, so it seems to work now. Good work, everyone. Let's go home. Champagne, perhaps. So there's still a bug. I'm sorry. There's still a bug. So let's try and see if we can use some other testing technique, because I'm already bored in writing these test cases. I've written them over and over again. And that is the problem of manual test cases. I need to rerun the test every time and doing manually, so I will forget about different inputs that I've made. So let's end that and let's automate things, perhaps. Let's do that first. This is a quick automation of this test. So instead of inputting things, I've just written a piece of code that takes an array. I've written expected output was 4. The exercising of the system under test was this line. I call the method getMax. And then I have this if statement. And then I also have some system out that tells me if the test succeeds or not. And I run that. And it says test succeeded. And it's pretty easy to run regression test that again. Test succeeded. It's effortless. And I can even do this thing. It's always nice to copy paste code, right? Let's see if we find, if I put that as a 5, then it should find that, and the expected output is 5, and I can run these naive tests, and both tests succeeded. Fantastic. And I can run these over and over again. Okay. But suddenly I don't have enough information to find the next bug still. I could be writing these tests up and down. And so let's do some automation of generating new input. And in this case, I've written such an implementation. This is random testing.java. It creates an array of just a random sized array, the maximum of 1,000 numbers in the array. And then it puts, it puts numbers in this array somewhere. Here it puts the numbers in the array. It actually calculates the correct expected output also as the maximum of these numbers. And then I run getMax on this random array. And then I can do that over and over and over again. So I generate a new random array of random size with random items in it. And then I actually calculate the correct value for each of these. And then I compare the actual output with the thing. So let's do that. Let's do that 1,000 times. And random testing. Oh, So in 2 cases, I get an error. So we have conducting 1,000 tests with arrays of size 1,000. We got 998 successes and 0 fails, but 2 errors showed up. Reliability, do you remember reliability? If we take a random input, the reliability is the probability of that to be a successful run of the program, or the reliability is the amount of successful compared to the amount of fails for inputs. So we got a reliability of 99.8%. It's an estimation of the reliability because I'm just using these really small arrays with 1,000 items in them, and the size of the array was huge, right? It was like 2 to the power 32 minus 5, right? That was the largest Java arrays that at least according to Stack Overflow, that we could do. Let's manipulate that. Let's make it 10,000 items in the array. Let's see if that changes something, and let's rerun things with that. We said, oh, the reliability changed. We don't get any errors anymore. Let's change that to 100,000 items in the array. But it's starting to take some time to run these tests, right? Still 100. Let's add 1,000,000 items in the array. And yeah, so and it's starting to take much longer to run these tests. Still 100% reliability. I have not changed the code, so we know that there are bugs, but because we found that during the first thing. So so let's see if I can fix this. Oh, no. Why? The Control-Alt-S did not work. Settings, preferences, editor general. Perhaps there is another way than Control-Alt-S, because that did not. I'm just going to change the size of the code. Perhaps this settings is somewhere else. File, thank you. File settings. You're never as blind as when you're giving lectures. And then we have editor general. Editor general. And then we have make sure that setting change font size, zoom. Change font size. Control plus mouse wheel. Okay, let's try that. Ooh. Thanks a million, Pompe, for giving me that. And I guess that everyone agrees with that was a really good move. Okay. So we knew there were bugs here, but increasing the array size did not help us find these bugs. Perhaps the number of tries does, so let's add 10,000 tries, but I don't want to do that with 1,000,000 items in the array because that's going to take forever. So let's have 1,000 items, which I think was what we started with. So let's run that again. 10,000 tries. Yeah, it seems that we're discovering this bug. Now we could have some mechanism so that I can start the debugger on the cases where something fails, right? And then I can start those, or outputting the actual input in those cases could be an interesting idea. But let's not do that. Let's keep. So random testing was generating input. We could do random testing on unit testing, but it seems a bit flaky. You remember the word flaky? If we get different output from the test case depending on the run and not the actual code, then we have a flaky test, and that was, yeah. So let's go back actually to the lecture instead, and and talk about test automation, because we've already started a bit on this. We have seen that manual testing is boring, not that super boring here, but it can be, trust me, it can be really, really boring to run the same test for the 100th time. And if we're bored, we tend to make mistakes. We tend to try to simplify things by just ignoring information that we see and stuff like that. So we're not doing a good job. So automation is really the way to go. I'm not really talked so much about executable specification, but I've told you that it's probably a good idea to name these tests so that we get good information. We've also seen the need for accuracy, right? And that is that each test case precisely points to the problem. The first test case, after a while, I've designed the bug so I knew what it was, so I could actually fix the problem while you were looking, and you probably only half saw what I did, right? But perhaps you didn't see the other bugs, I don't know. But in other cases, the random testing did not, at least the feedback that I provided for my random testing, did not give me enough information to pinpoint the error. And we also have a problem that we need to solve with this test automation. We need to know, actually we need to solve that even if we do manual testing. We need to know if we're doing a good job or not. So, testing tools or frameworks, and I call these X-unit frameworks. It could be JUnit, it could be NUnit, it could be almost any, framework for writing tests. It could be these BDD frameworks also. For Java, we have JUnit. It's sort of the I don't know, the first framework perhaps. I don't know, the most famous one at least. .NET, we have NUnit, we have Microsoft Test Framework, something. You install that, right? You use X-unit, okay. For PHP, we have PHP unit. We have the framework that I wrote for CS Quiz that some of you have tried now, called Tdd for some reason. We have PyUnit for Python. For JavaScript, there are all these billions of different frameworks for conducting testing. So these frameworks, they provide different things. And the way that we write code with a framework is that we perhaps inherit from some class, and we write methods in a special way. So in Tdd framework, you inherited from the class, I think test class it was called, something like that, and then you wrote these public methods that needed to take an argument, and those become test cases in CS Quiz. So we have these test classes, and we write these assert statements, and you've seen those in CS Quiz also: assert true, assert false, assert equals, expect, exception, different things like that. Not in Tdd, yeah, it actually exists in Tdd also, but frameworks usually allow us to build different suites of tests. So we can have different suites of tests for different programmers perhaps, or for different parts of our program, or for different test strategies. So for instance, you could have a suite of tests that you run each time you compile your program that is really, really fast, and then you could have this slow suite of test cases that you only run just before you push it on GitHub or something like that, or that you run during night or something like that. Some of these frameworks or some other framework or add-on to the framework also gives us mean to get something called code coverage. And we're going to talk about that because that is important to assess the quality of our test. How good are we doing when we're testing? Then we can use some code quality measure for that. And this last part is mocking, and it could also be a means of handling problematic things when you're testing. A framework usually also provides a means of running these tests. And on the right-hand side, this is from Eclipse. And we can see a test report where it says that we ran 18 tests, 1 failed and 1 error. And here with error, I think that means an exception has been thrown or something got, perhaps divided by 0 or something like that. And this failure is when we get a different output from the expected output. So we can see all the tests for these parts succeeded, and then the port test port too large, that one had an error, and test port OK, that one failed. I get a question. Can random testing be seen as a way to investigate if you can be happy with your selection of tests or if more is needed? Or when should you actually use random testing? I think that in the case that I had, where I have a huge input space, that is a case for random testing. When the input space is huge, then let's take some samples in this input space and let's see if there is a problem. I mean, I jokingly said that 1 million items in the array was taking too long to run, and because it was taking seconds. But actually, random testing, you could do that overnight. Or you could let it work for a week or whatever time we have and just generate random test cases all the time. And if it reports good enough information back to us so that we can repeat these failing test cases, then we could have a server standing just running random testing all the time for us. So it's a different testing technique. It's not always applicable, but if you have this well-defined input where you can generate random test cases, then by all means do random test cases. If we have a more limited space, if each input instance is very complicated, then perhaps it's not that easy to generate a random tester for this. Hopefully that was an answer to your question, Therese. Thank you for the question. Okay, now we know sort of what we can expect from an XUnit framework. So before we check hard to test code, I want to go back and let's check some JUnit tests for the MyMath problem. So here I'm using JUnit something. I think this could be, I'm not sure, JUnit 4 or 5, not really sure. I think this is JUnit 4 actually. Okay, so I have a test class, and in this framework, in JUnit 3, I think you inherited from a test class. In this case, instead, we're using these are called something with an A. In this case, you have this at before for some methods, and you have an at test for the actual test cases. You can see that I've used a soot, an instance of the class I'm intending to test, and I call that system_test, SUT. That is a private member of this class. And then the testing framework provides a before method. I call that setup, that it's It doesn't need to be called setup in this case, but it was called setup in JUnit 3, so I continue to do that. So before is run before each test case. It's sort of like the get system under test instance that you were that CS Quiz needed for the TDD framework. Yeah, it's Kenny says that it's called attributes. Yes, these before. Thank you. Annotations. I don't know. Annotations. Okay, probably annotations. And so in this setup method, I create an instance of the system under test. So that happens before each test case. And then I run the test cases. And you can see that the first test case has an input array, 1 and 2. And I assert which one is highest of that one. I actually created a private, specialized assert method called assert highest. And that one is in the bottom here. So it's called assert highest. And that one takes an array and checks or exercises the system under test by calling the method that we actually want to test. With this input array, we get an actual back, and we can see that the expected value is always 2 in this case. Zooma till? Sure. Something like that. So the expected value is always 2 in every test case. And it compares the expected value with the actual value using an assert equals method. And this assert equals method is from the framework. So I've created my own test or assert method just to remove some code duplication. And this makes it very easy to write unit test because I only need input and I need some to call this method for each test case. It becomes very easy to add new test cases. And you can see that I've also used a naming strategy for the actual name of the test case. So if this fails, then I can read the name of the method of the test method in order to understand what is the problem. Should return the last highest value. So the last value is the highest. And then I have some complementary test case for that. Should return the first highest value. Not super good naming, right? Everyone who took the course 1DV610 something perhaps frowns upon these names, but the intention is that the first item is the highest, the last item is the highest. Should return the third highest value, so let's have an array with a negative item and let's have the highest last. Should throw something, should throw exception when input is empty. So that we have an empty array, and that was all the test cases. So let's run these, and I run these by using, and it's building, it's parsing, it's running. And now I get a test report back from the framework, and we can see that should return the first highest value, should return the last highest value, should return the third highest value, all succeeds, they are green, and then I get a failing test case, should throw exception when input is empty, and that seems to be the problematic case. We can see that over to the right we get an unexpected exception, array index out of bound, 0. This means that if we have an empty array somewhere, I index 0.0 in this array, and now I can show you the code again and see that I'm actually having a bug on line 17 here, where I index the input array on place 0. So if it's empty, then we get this exception thrown. And I've actually just moved this if statement, which checks for empty arrays and throws an exception for those, up there. And it's very easy for me to, after changing the code, regression test by just pressing the run button again, and we have fixed the problem. and I regain confidence in my code. How do you know the errors in your program code and not in your test code? You get more confident in your code by testing, but why should you trust your test code? I think this is a really good question. The problem can be in the tests. The problem can be in the specification. As testers, we need to be creative, we need to be intelligent, we need to read the specification, and we need to criticize our own code. And sometimes the problem is in the test. So let's answer the question. What I usually do is when I write a test, I try to make the test very simple. I try to make it as simple so that I'm not prone to make errors. If I write complicated code, lots of statements, lots of if statements and for loops and stuff like that, then it's very easy to make an error. But if I write just 2 lines of code, then it's easier to be correct. Thing to be correct, I can still do errors. But in the case here, I would say that it's pretty easy to do a correct test case in this case, right? Because it's a simple method. And we should strive to write simple code that is easy to test. But this is a real problem. I mean, sometimes the fault is in the test. Sometimes we make an error in thought or in action. And we introduce such bugs also. The case, I think something that is related to this is in the random testing application. Because in the random testing application, in order to find the expected value, I actually need to calculate the correct value, right? So this code, where I check the expected output here, is actually sort of the same code as in the system under test, right? So this becomes a bit weird. I'm writing some code to test another code. And so this is sort of a bad practice. In some cases, we could have a simple way of producing input, like this one is pretty simple, and then we have a complicated way of doing this in the system under test. For instance, if we calculate pi or something like that, so we calculate decimals in pi. Then that can be done in a simple way, and that can be done in complicated ways. So let's choose a simple, slow way, perhaps, to do that in the tests. And let's use that as feedback if we're doing the complicated way correctly. So, you can do these kind of things. But of course, you can have problems in your test. And you can watch the screen as a manual tester, and you can be wrong. You can make an error, right? Same thing. Okay, so now you know test frameworks a bit. So let's talk about what is not super easy to test. Some of these are sort of hearsays and things that I've come up with that perhaps don't become problematic for you. But for me, error handling was hard to test. And the reason for that was that this error handling code was never really executed. So, and it was really hard to generate input so that an error was called. Because I've tried to write the code so no errors would occur. And that meant that in my game code, in this case, is the one that I'm thinking of, I've never really ran that error code or error handling code because that didn't happen. So it was sort of meaningless, dead code, sort of, and that was never tested. So what I I changed the way I'm writing code, and nowadays I'm using exceptions mostly. And I usually try to test what can go wrong first before I test what should happen. So I write a lot of tests for perhaps invoking those exceptions in the system under test. So let's send an empty array into this method, and let's make sure that it throws wrong input exception. Let's do that first before we do the other things. So that is sort of the strategy. If you have outputs to console, and this is actually the last point also, or the output buffer in PHP, or the console log, or the system out in Java, then how do you test that something is outputted on the screen, sort of? How do you test that works? And it's actually pretty simple, because console or system out is an object. So we need to use something called mocking. And I've already given you the word, and we're going to talk about that. Complex code with many if statements, perhaps nested with for loops and stuff like that, becomes hard to test, because it's hard to find all paths through that. And we're going to talk more about finding paths for things later in the course. And the solution for that is pretty simple also. Don't write such code. So if you have a method with a for loop, and then you have some if statements in that one, perhaps you extract a private method or protected method for the if statements. And in the for loop, you just call the private method. And that code suddenly becomes easy to test by behavioral testing using a mocking framework. So writing more clean code helps us. And this is actually one of the reasons that assignment 1 part 2 is written as it is, because I want you to discover that if you write complex code, then you're having a hard time completing that assignment. So it's probably is one of the realizations of you, I hope at least, that you will realize this, that you need to write easy methods so they're easy to test. Code with dependencies is harder to test than code without dependencies. So if you depend on, for instance, a database or whatever, then this needs to be considered when testing this. And we said that we want to test things in isolation. You've done an assignment, hopefully now, in CS Quiz, where you need to test one class and not the other, and find bugs in one class so that we have accuracy. And we can get direction feedback so that we can test one, know that we're going to fix this problem in this class and another problem in another class. So we're going to use dependency injection and mocking in order to solve that. Static code, don't have that. Remove the static keyword. Don't have these weird dependencies or static dependencies. Just remove those. Don't have these singletons. Singletons makes things harder to test. Don't have them. Don't use them. It's bad practice. Databases, files, things that are... we need to manage dependencies to things in order to get easy to test code. Code with side effects, and I've already talked about system out and console log and stuff like that. It's harder to test than code without side effects. A side effect is something that happens when we call a method that is not really specified in the method name. You cannot really understand from the method name. It could be that you call something to system out, that this method was called. It could be some debug code that you've added or something. So that code is harder to test because it's not really stated in the name, and you need to read the code. You need to do white box testing. Oh, we already talked about that, really. How do we test system out, echo, and console calls? And the thing that we have, if we have code that calls something to system out, is that we're using a component. System out is a component, or in echo we're using the output buffer in PHP, or console log, we're using the console object in JavaScript. And we have a dependency to that one. So the solution of dependencies was to solve by mocking, it says here. It's the same thing as we did in testing as isolation. We replace the dependency by something that we can, during the test, control. So if we replace system out or echo or console log with something that we can control, then we can check with behavioral testing if a call to that specific method was called. So if you have like a call to print line on system out object, and I put in a fake system out object that I can control, then that is used instead of the system out object during the run of the program. And after I have exercised the set, after I've called the method that I'm intend to test, then I can ask my fake object, was there a call to print line on you? Did you receive one such call? What kind of parameters did you receive on that? And that is my actual assert statement. So I'm gonna show this in using Mockito in a few moments. What about in or other input? Yes, so you can use mocking in order to fake input also. So if I have input into my program and that input comes from perhaps cin or system in Java, then we can replace that with a mock object, a fake version of that provides inputs. So if we call getLine or whatever it's called that gets some input from the user, then it actually provides what we configure the test to provide in that case. And I'm going to show that also. So just you wait. And this is sort of on the same path. We're going to need a break really, really soon, so you don't fall asleep too hard. But I just want to build up some suspension before the break, and then we're solving these problems after the break. So if we have a database, then that is a dependency. And one of the problems was sort of the same as with the random testing. If the input array was too large, it took too long to run it. And I didn't want to do that during the lecture because I don't want you to wait for a test result during the entire lecture. And if I have a database, these database queries take time. They take these horrible milliseconds or even more. And if I run the 100 or 1,000 tests against a database, and if I have really complicated questions, these can take really long time. And I was told by a German car manufacturer tester expert, and he said that, okay, we're not really running unit tests that often, because when we're going to run these, we need to set up all these specialized servers that are costly, like in 10 million euro class. And then we start the servers and we come back 2 weeks later and look at the result. Because they needed to do a lot of tests and there were databases involved, and it actually took 2 weeks of runtime to run these tests. These were pretty much a bit more complicated than the test I want you to write. And these were probably higher at stake. I mean, car manufacturers really want their code to work, so they probably did a lot of testing. And I'm not sure really what they did, but he said that the databases was the reason for this take so long. And the reason that a database takes so long to run is perhaps it's on another computer, so we need to do network communication to that one. Then we need to translate from these queries, SQL queries, or in best cases we have some prepared thing that we can run that is pretty much an executable. But it's still code that needs to run, and the database is just having these files that it needs to open and entries in different files. And if we're making a selection with some weird query, then it's actually code that runs on these to make this. And it's smart code, but it can still take a lot of time. So how are we gonna handle this? Because when we run our test, we want it to be really, really quick. And one way of making it really, really quick is to remove everything that takes time, such as a database. So when we unit test and we're not really accessing the database at all, we replace that with a fake database. Something that is super fast. Something that when I ask it a question with a selection statement or whatever, it just directly returns what I want. So again, mocking. Yeah. So I think that, yeah, and this is the last slide before the break. So if we have a troublesome dependency, remove that during test and replace that by a mock object or a fake object. And dependencies also had this problem with accuracy, that we don't know if the problem relies in our component that we're intending to test right now or in the thing that we're dependent on. And the solution is to inject these dependencies. So perhaps in the constructor of your method, inject these objects that you're dependent on, so that when you write your code, you can replace whatever you injected with something that is just the fake thing, that is super fast, the mock object. Yeah. So let's take a look at Mockito and mocks, but after a 15-minute break. Okay, welcome back. So we were talking about mocking as and I sort of presented it as a silver bullet solution for everything, almost. And the reason for me being so super positive about this was that I tried to do both test-driven development and I tried to do unit testing, automated unit testing using these frameworks for a long time, and it felt like I could never really succeed in doing this, and it always backfired in some way at me. And then someone told me about mocking, and then I discovered Mockito, and most of my problems just solved itself by this. So it was sort of that experience that I had, and it doesn't mean that you need to have the same kind of experience. And I mean, there are people who are not using mocking frameworks at all and feel happy about unit testing. But that revelation that I have is sort of the reason for you needing to use mocking in assignment 1 part 2. And also the reason for these isolating test things in assignment 1 part 1. Okay, so mocking solves two big problems. First is that, okay, we want to test behavior. What do I mean by that? So let's take a piece of code and let's take a look at the run menu round here that I wrote last week. So the first thing that happens in run menu round is that, okay, we have some kind of view. This is the dice game. You're supposed to roll a dice and then you're betting on the result, sort of. And the first thing that is supposed to happen is that we're going to show the menu. And then we have an if statement. If user wants to quit, then we show quit message. If we show quit message, then we don't do anything other things. We say, okay, welcome back next time. Bye-bye. Hopefully you can recover from all your losses. And if the user does not want to quit, then we ask the user to do a bet, to put in some money or whatever. And we do that by calling a method called showBetMessage. And then we call a private method called doBet to handle the actual betting thing. How do we test this method? It doesn't have any output at all. It has a lot of interaction with another class, a roll dice view instance called view. So as I've said before, we dependency inject that dependency. So this is the constructor, so we dependency inject the dependency through the constructor. And you can see that I save this thing here. And then I really want to test behavior instead. Instead of testing an output, I want to test that show menu was called on the view object. So that is the test I want to write. And then I want to ask, was user wants to quit called? And those are the things that I want to test. And then I want to test that if this one was true, then this method was called. If it was not true, then this method was called. And this method was called. So sort of other things than the output testing. So the expected behavior is not a return value in this case. It's that this method was called. And that is called behavioral testing. So test behavior. So Mockito solved that problem for me. And the other thing was that if I have a difficult dependency like a database or in this case a view, then I just replace that with a mock object instead. And this is sort of how it works. We inject a mock object. And this is the one of the tests for this. And there are two parts of this and there are different places in the file. But you can see that in the file I have private roll dice view, a view mock. So the mock object is of the same type as the actual object. It's sort of like it inherits from that class. So roll dice view is the thing that I actually have a concrete class of. And here in the setup method, which was called before each test case. I create a mock object of that. And this is the syntax of Mockito. So, but really what it does here is that it takes the roll dice view class, and then it creates a fake class that has all the methods of this one. And that works like that class, but in each and every of the method, it's sort of empty. And it depends a bit on the mocking framework how it does this. But then I can configure that class to work in a specific way. And that was the replace difficult dependencies, because I needed to configure that class. So I can say, and I do that in the beginning of the test, when user wants to quit on the view mock, when that method is called, then we return true. So I sort of write code in this mock object by calling methods. And then we exercise the system under test just like a normal test. Sut, run, menu, round, that was the method we called. And then we have our assert method, and it's called verify. Don't mix up this with verification. It's really an assert method that a certain method was called. And we say that show bet message should never have been called on the view mock object. That is the test. And if we read the, you can see that I use another kind of syntax here for my test cases. Run should not show betting message when quit. So I configure that the view so that the player actually presses on the quit button. And I do that by this thing up here. And then I verify the behavior is correct. So do you remember the code? That this actually tests that this method is never called if this one returns true. That is the test case. So let's take a look at other tests of this method. And yeah, so run should call menu. And what I do is that I call the method that I'm testing. This is the exercising of the system under test. Run menu round. And then I verify that this method, show menu, is called on the view mock object. That is sort of my assertion. That is the test that makes sure that this method is always called. And this is called behavior testing. We're testing that the behavior, that we're talking between these objects in the correct way. We can think of talking between classes as a protocol. First, show menu must be called, and then user wants to quit must be called. Depending on the result of user must quit, then other methods should be called. Show quit message or show bet message. And if we take a look at my tests again, we can sort of see that that is how I designed this. So run should ask if the user quits. So that is a test. The name of the test gives me some clues on how to solve this. If it did not call user quits, user wants to quit, then I get a good message back. I again exercise the system under test. This one has already been configured with a mock object. You check it out over here. So I create a view mock using the mocking framework's mock method. And then I dependency inject the instance into the roll dice game through the constructor. So now I've configured the system under test so that instead of having a dependency to a real roll dice view, it has a dependency to a mock object that I can configure. And this happens every time. Yeah, and the next method, run, should show quit message when quit. In order to do that, I need to, the show menu I've already tested that, so I don't test that again. But in order to show the quit message, I want this one to return true, and then I go in here, and this method should be called. So let's take a look at the test. When view mock, user wants to quit, then return true. I configure the mock objects so that I get this is sort of the input, right? The input comes from another object, really. So it's sort of the same thing as if we input numbers or whatever into our class, but it's just that the dependencies we have, if we call methods on those, this is how they input things into our system under test, the thing that I want to test. Then I call exercise the system under test again, and then I verify that the quit message once actually shows up. And then, in order to make sure that the quit message does not show up every time a user does not want to quit, if a user wants to play, there should be no quit message. So when a user wants to quit, we return false. That was the configuration of the thing, our input. And then we call the exercise, the system under test, and then we verify that this quit message was never called. It's a bit weird syntax, and sometimes in these testing frameworks they're using something called synthetic sugar, and that is specialized structures of the code or of the mocking framework's code so that we can write these in a more fluently way. I don't mind this way, it sort of works for me. You need to learn how the mocking framework works in order to work with it. But they're really designed often so that it should be easy to read these. If we continue, run should show betting message when we continue. And now suddenly I introduce this continue subject, so that means that we don't quit. So when the user wants to quit, when we ask that of the mocking object will return false. And then exercising the system under test, and then we say that, okay, if the user does not want to quit, then we show the betting message. Again, we have, if they want to quit, we should not show the betting message. As you can see, I'm always creating both branches. Make sure that this shows when this happens, make sure that this does not show when the other thing happens. You can see that I'm a bit precise with this, right? I'm very trying to find all paths, trying to test every aspect with a single test case. I want each test case to test one thing. I want, if there is a bug, hopefully just one test case will break also. I cannot promise that. Okay, let's continue a bit. Run should call do bet when continue. Now we get another thing. If we take a look at the code again, we've already tested this one. We've tested this behavior and this behavior and this behavior very carefully. So almost all combinations, right? But now I have a private method. And well, it's actually public, I don't know. Could be made private, I don't know. I didn't dare to make it private probably, because I didn't know how that worked and didn't want to learn yet last week. But I'm calling a method on my own object. And suddenly it becomes hard to mock, because then I need to mock my own object in order to make sure to test if this method was called or not. And for these reasons, we have, from Mockito at least, something called test spies instead. A test spy is actually a mocking of your own object. So the test spy allows us to verify that calls on our own object was called or not. So let's take a look at the test. The configuration of the view mock is the same. We're still mocking the view. When the user wants to quit, we return false in order to step into this else part of that statement. If we take a look at how I create a spy, because I use a spy object, you can see that I create a system under test. I inject the mock object as usual, but then I create or call a method called spy on the Mockito framework. And I introduce this object. And now it creates sort of a basket or something that is around my object. So to make sure that I'm still calling the code on my object, but I record everything that happens. And that is what the spy does. It spies on the object, right? And you can see here that now I'm not calling the method on the system under test anymore. I'm calling it on the spy. And after I've done that, I can verify, or I can check the behavior of the spy that it called the method resolve. Oh, no, I'm actually too far away. I call the method run menu round on this one, and then I check that it calls do bet. That was the correct version. I was already down in do bet here. Okay, so this is a bit weird. And these are the things that I want you to work with in assignment 1, part 2. So dive deep into the mocking framework of your choice. Learn how to use that in its syntax. So you can use Mockito and JUnit and learn, okay, these features exist also. I need to dive deep into these. Or there could be cases if you take a mocking framework, there are no spies in that one. I mean, you need to learn your framework and become an expert in that. So now I've created sort of a complete test suite for this one. There are perhaps cases that I have not covered. I don't know, but I tried to make a test suite for this method that tests its behavior in such a way that if I do a single, let's just run these tests. Yeah, they all succeed. And I tried to write it in such a way that if I destroy the code here somewhere, I hope that I get a message down in the test output or the test results that actually helps me to show to see what is wrong. So let's read that. Run should show betting message when continue. Okay, that was the exact thing that I've commented out, right? So let's comment out another line and see if this works. Now we should have something about show quit message. Run should show quit message when quit. Okay, it doesn't do that because I commented it out, right? So this is the goal. Hopefully only one test should fail for each error that I possibly can introduce. Of course, if I do something like this, then I'm gonna get more errors. But I mean, that is everything that I don't do. I'm still getting some successes. You can see that run should not show quit message when continue. I mean, it doesn't show quit message anytime. So we can have a good test case, because this is a good test case, that succeeds even if there ain't any code. And you've experienced this when you worked with CS Quiz. Even if you didn't write a single line of code, there were test cases that were green. And you need to understand the connection between the tests and the code, the implementation, in order to successfully interpret the message here. But ideally, we only want one test case at a time too. Okay, hopefully you got some idea on testing behavior, and also to replace dependencies and how to configure these now. So now we at least seen an example of Mockito, but you really need to read the documentation of the mocking framework of your choice in order to do that. Okay, next part. Am I doing good when I do my testing? Can someone trust my code when I'm doing my testing? So how do we know that, how can we how can we get this confidence? In the method that I just shown you, I'm pretty confident that that method works as specified, just from the test cases that I've shown you now, right? And I feel, I don't know, but perhaps I've also introduced some of that confidence in you. But there are parts of the same project that does not work, that are not tested. The view itself is not implemented, is not tested. So there are problems. And we need to take a look at the large project and be able to find the pieces that don't work, that are not properly tested, so that we can create tests for those, so that we can build confidence in the entire thing. And the sort of solutions are to run some kind of coverage measurements. And I'm going to show coverage, and let's just run a roll dice game test with coverage. And hopefully, I've just done this once before, so probably not going to work. Okay, now I've run all the tests, all succeeded, right? So everything looks right, but we still don't have any test for the roll dice view, which I haven't got any implementation of that either. You just like return 0 and return false, and all these show quit messages that perhaps should have system out print line things in them are not doing anything. So we really would like to see that this has not been tested, this has not been implemented. So if we take a look at the coverage measurement, we can say that 100% of the classes, 73% of the lines is covered. If we take a look at the project as a whole, both classes looks like they are tested, but really only one are. But if we take a look at the methods, only 44% of the methods are called. This one contains only 2 lines of code, really. So 73% of the code is actually tested. If I open this, we can see that roll dice game, the methods in that is fully tested. All methods are called. All lines are called during at least one test. But the roll dice view is 0 methods called and 16% of the lines are called. So here clearly we can see what is tested and what is not using coverage. How this is done is that when we run the program with coverage, or we run the tests with coverage, the code is compiled in a specific way. So in the beginning and in the end of each method, let's see if I can roll dice game, this one. If I want, for instance, method coverage, then I could get method coverage by introducing a statement here and like logging that this method has been called, right? I could like write to a file and see that run method round has been called on this one, or I could like system out print line like that. And then I run the tests, and then I take a look at system out and see if this line is there. Then I know that this method has been called during the tests, right? So that is sort of what happens when we run with coverage. So on every line in the code, there are logging lines introduced that make sure that we can get these statistics on how much of the code is run. This is a bit specific, and much of the course literature covers that, and we're going to talk more about that in the future. There are different types of coverage. I'm going to give you the line coverage, or actually the class coverage did look, it was a bit not too, it was a bit too coarse-grained it actually said that the class coverage said that the view class was tested when it was not. The method coverage showed that 43% of the methods in the view method was tested, but it was not. And the line coverage showed most of the truth. So when you get more fine-grained coverage measurements, you get better information to make your judgments from. There are different types of coverage. What we have done here is just line coverage. We might want to make sure that if we have an if statement, that perhaps both paths of the if statement has gone through. If we have a loop, perhaps we want that loop to be covered 0 times, 1 time, and more times, and stuff like that. But that is later lecture. Another way of seeing if we're doing okay is what I do in CS Quiz. And what I do in CS Quiz is that the code that you write is not really that interesting in CS Quiz. The tests that you write are interesting. So how do I assess your test suite that you wrote in CS Quiz in assignment 1, part 1? I do that by having different implementation. Some are correct and some contains different bugs. And if your test suite passes the correct one and find each of the bugs, then your test suite is doing a good job, right? So if I have a bug, whatever bug, and your test suite finds it, that is a good thing, right? So mutation testing takes this to the next level. So mutation testing takes the implementation and then it randomly introduces bugs into that. Then it runs your test suite and see which of these bugs do your test suite detect. And then you get a percentage like, okay, 50% mutation score means that 50% of the mutations were found by your test suite. And a test suite with 100% mutation score is much better than one with 50%, right? It has a bug detection power thing, right? So the first one was that we make sure that parts of our system is executed during tests. The second one was that bugs in the systems, the mutation testing was bugs in the systems are detected by, or bugs that could be in the system are detected by our test suite. And then we have checked coverage, and it's way more complicated. It's like this. We're going to talk a bit more about all these things later. But checked coverage says that if you have an assert statement, all the lines of code that contributed to that assert statement getting the result it got, those are called tested. So if I have, I can have a test that runs all code but don't test anything in it. I would test without an assert statement. And that could get 100% code coverage. I could call every method in my project, but I never assert anything. I never test really anything more than that it does not crash. But checked coverage makes sure that we only count lines that are actually contributing to the test result, so to speak. It's a bit weird. I get a question. So it's better if I improve my CS Quiz exam so it doesn't just pass all the requirements, but also account for bugs that aren't in the code at this moment. So should I spend more time in CS Quiz or move on? So if you get a passing on CS Quiz, then that is enough. You don't need to create more tests than CS Quiz becomes green. The 2 examination tasks in that one. So in the view that you have showing all the tasks, it should say something that you're past this assignment. It probably does, right? Something green should show up. Yeah. So you don't need to work anymore with that when CS Quiz tells you that you're done. Because I've only created some mutations of the code. Mutation testing has problems. All these have problems. Mutation testing has problems like if I mutate the code, and the code still does the same thing as the unmutated code, then that mutation cannot be detected by your test suite because it's not a bug. It didn't introduce a bug. It just, yeah, changed the code in some way that did not change the behavior of the code. But let's not dive too deep into that. We've already seen that code coverage can be seen as some kind of statistics as the one below. This is from Eclipse, from some version many years ago. And in Eclipse, you could also get to see which lines were covered or not. I don't know if I can get that in the tools that I've shown you right now. But in this case here, it's very clear that this throw new illegal argument exception, this line was called during one test at least, but this is okay, return false, is not tested in any test case. That method was not called, so that line is not covered, so I need to add more tests for this one. And I can see that this also here in the test report. Yes. So I think that sort of is it for that part. And now we're going to talk about agile testing, and then we're going to talk about test-driven development. But I think you need some time to find some coffee and perhaps relax a bit from your bleeding ears from my voice, whatever. So see you in, should we say 10 minutes? Okay, welcome back. So the next part is about agile testing. It's just 2 slides really. You're supposed to watch the video of the lovely lady talking about her experience in agile testing. And this is just, be a bit careful when you listen here. I'm taking an entire industry and just saying that everyone does the same thing, and it's not the truth. It's overgeneralization and simplification and stuff like that. But let's say that before agile testing, if there was a line that we could draw, and it isn't, then, okay, we had some requirements. These requirements led to testing, perhaps mostly to system testing, so that we created test cases for where we run the entire system instead of unit testing. This is not a complete lie, but it's not the entire truth. But usually testing came after the implementation, so that we implement the code and then we conducted testing. We wrote our test after we implemented it, and it's sort of the waterfall development process story, really. We had specialized testers who often came into conflict with the programmers. They were not on the same team. Perhaps we had cases, and I interviewed a tester, I think his name was Olle, and he told me the story that the testers, they got bonuses, they got extra money if they found problems. And they had this bonus system where the programmers did get extra money if the testers did not find any problems. Such incitament just builds the foundation for collisions and separation, and you sort of hate the people who find the problems in your code instead of you being a team. But watch the YouTube video of the lovely lady, and she will sort of tell you that again. Problem, I've already told you about turnaround time. Turnaround time is the time it takes to you release a product, and then you test it, and then you fix the problems discovered during the testing, and you release it again. That is the turnaround time. And the turnaround time for this could be very, very long, many weeks or longer. And in many projects we have a huge turnaround time, and the end users of this system experience that it doesn't matter if I report a problem, because I'm not going to be in this position in my work when the bug is fixed. So let's not do that, because it takes too long. I mean, weeks is the small number here. Years could probably. And I've felt that with systems here in the university, where I don't feel that it's worthwhile for me to report bugs. If I can circumvent them, if I can work around them, then I do that instead. Regression testing that we talked about, which is retesting something we've done before, was painful because it takes weeks, and perhaps we have a lot of manual testing. We actually had manual and automatic testing because it's so painful, so let's automate the process. But still, if we do this automation on the wrong level, then we get flaky tests that fail for the wrong reason, and we need to update all these tests again, and that makes it frustrating. And so, still a bit made up story that I take an entire industry and just put it on two slides, really lying a bit about them. So with Agile testing came as a reaction. We cannot have this situation anymore. We want something else, and we sort of want to solve these problems that we had before. So requirements still leads to testing. We still need some kind of specification, but testing happens earlier. We test during our implementation, and perhaps even before we implement. We write tests so that we know that we're doing the right thing, because we need that confidence. Suddenly, we invite the testers into the programming team so that we can work on the same team. We want, as a team, a good product. We have some other mechanisms for giving people bonuses instead of things that make people clash. We want shorter turnaround time. We want it to be seconds. We want to run the tests really quickly. It takes a short amount of time, and then we can fix the problems that we find. Perhaps programmers can do that on their own computers. And so short turnaround time requires quick and painless regression testing. In order to get that, you need to automate almost everything. We focus on automation in order to do that. So JUnit is sort of a thing that came with this. And I mean, it's an old thing, so Agile testing is an old thing. And again, this is an overgeneralization of an entire industry, so take it for what it is. So test-driven development came sort of together with this. Test-driven development felt that, oh, we're writing tests, but they're really hard to write, and they're flaky, and we have all these problems with the tests. So it's sort of, if we write the implementation first and then write the test, it becomes complicated to write the test because the implementation is not designed for testing. But if we turn this around so that we test first, we write a unit test first, then we can design the code after how it's tested instead. So that is sort of the switcheroo here. So test-driven development is test first. It's a low-level software development process. It tells the programmer what to do in his daily work. Most software processes is on a much higher level. It's about, first we have this part of the iteration, we're going to work with requirements, and then we're going to work on the design a bit, and then we're going to implement a bit, and then we're going to test. And that is in one iteration. And then we do that again and again and again and again. Test-driven development is as much about designing the software or designing how the code should work as it is testing. When we write the test first, we're using a top-down thinking of the code, and we're inventing how the code should work. Otherwise, we become test last. So in order to become test first, test-driven development is mostly a design thing. And you're designing the code on a low level. In this course, I'm using test-driven development in assignment 1, part 2. And that is because I find it a very good way of learning unit testing frameworks, a very good way of learning how to write code that can be tested, a good way of learning these mocking frameworks. And it's not a silver bullet. It's very awkward. It feels in my entire body when I program in this that I really don't want to do it. So I'm going to push you through this with assignment 1, part 2. And the reason that you don't need to do that assignment for more than higher grades is this. It's awkward. It's going to feel awkward. So please bear with me and try to do this anyway. It's not a silver bullet. I'm going to show that in a couple of slides here. And you don't need to do this after this course if you don't want to. For some cases, for some certain kinds of code, I still do it because it's awesome for some kind of code. For other things, it's a bit weird. And without mocking, I will not touch it. Okay, so is TDD better or not? Some old research indicates that it takes longer to do this. You're writing more tests and you're writing tests first, and that takes longer than writing ordinary code. It's less bugs than projects without testing, perhaps. 90% relative, and this is just one case. There are other things that show that you get a sort of similar amount of bugs found as if you do test last. This depends hugely on the people programming. I mean, some people are very, very focused and very, very good testers, and that's going to affect these values. So it's really hard to do this kind of research. What I also know is that if we do, review the code, let's sit in a group and look at all the code, and let's see if we can find bugs by just watching the code. That is actually more efficient. To let people work in pairs, like in assignment 1, part 2, you're allowed to do the actual coding in pairs. I actually encourage you to do that if you can. That is also better to find this. I've seen this code by committee, so there are actually one person writing the code, and then you have all of these other people standing behind and pointing things to all the problems you do. You're not, so there are other ways that are perhaps more efficient in finding bugs. Okay, so let's learn how to do TDD. And the mantra that you're going to learn is red, green, refactor. Red means that we write a test. That test should fail. So you write a test, a single unit test for a piece of code that you want to test, and then you run that test. And if you're doing it the TDD way, that new test should fail. You're never allowed to write a test that succeeds. Why? If the test succeeds, then you don't know, then you cannot use this test as a measurement if you're making progress, because you added another test case. You're also adding another test case of something that was probably already tested before. So you must make sure that the new test case succeeds. Fails. Yeah, you see how hard it is. That's so awkward. So you run all the tests and it should fail. Okay, then you make a little change to the system. And this little change should be a very little change. Don't add things that are not testing in the test or in the tests that you have right now. Don't add the entire implementation. Just do one simple change that makes the new test case succeeds and all the test cases you had before that succeed. So you run all the tests and you should see them succeed after a while, right? Unless there is a problem in the test, of course, then you fix that. And as a last step, and that was the green, number 3 and 4 is the green phase. And then, okay, let's look at my code now and see if there is any duplication, if there is any code problems. Some of you have read the book Clean Code, so you know all about removing code problems. And that phase is called refactor, so red, green, refactor. And then you start over. Then you add a new test. And it should be quick, it should be easy, it should be done fast, and that should fail. And then you do a bit of implementation, and the new tests should succeed together with the other tests. And then you refactor again. And this is sort of how assignment 1, part 2 goes. So actually I'm adding more than one test here because I am stupid or something like that. Stupid example. So here we have Sudoku board tests. So we have a Sudoku board. And the first test, so let's just take the top one, is that I want to test that illegal argument exception is thrown if I create a Sudoku board with a null parameter. So really I want the Sudoku board to have a board coming into it, some array of all the places in the Sudoku board. And if you put a null, then an exception should be thrown. The second test is actually the same thing. I actually have it here for one reason, except making you confused when I say add one test. And that is the refactor part, because this other test, this redundant test, that tests the same thing, because the second test tests the exact same thing as this one, just in another way. So I run all the tests that I have, and you can see Sudoku board test. Both tests fail, actually, but the new one should fail. Then I make a little change to my code, and it's actually, we could remove the first line, the if statement here, and just throw illegal argument exception, and that should be the minimum change that makes this test succeed, because this test succeeds if an illegal argument exception is thrown. And then I run all my tests and see that they succeed. And then I refactor to remove the duplication. And here, the second test that I introduced actually is removed, because I don't need two tests for the same thing. So those are the phases. And then you do this again. Then you add a second test case. and then you add a third test case, and then you add a fourth test case. But you don't add more than one at a time. And then you do this cycle, and this should not take more than a couple of seconds to do. Yeah. And I mean, sort of the power of this comes from regression testing. When we've done refactoring, we can run the test suite again, and it should succeed again. So red, one test case failed. Green, all test cases succeeded. Then I do my refactoring, and I'm supported during the refactoring by the thing that I have a test suite that supports me. So if I fuck up during the refactoring, then the test suite is going to stop me from checking in that code. Then I can fix that problem also, because refactoring is a bit scary. So, yeah. So it's red, green, refactor. And this slide is more on how to do it in assignment 1, part 2. Because I want to be able, as an examiner, during the oral examination of then I want to look at the process you've used. In order to do that, I'm going to force you to make commits in GitHub. So you do red, you create a test case, and you do a commit. And then you write the implementation that solves that test case, you run all the test cases, and then you do another commit, and you call that green. And then you do a third commit after your refactoring. So that when I look at your GitHub repository, it's going to be like 200 commits in there, and they're going to be red, green, refactor, red, green, refactor, red, green, refactor. And once in a while, I also want you to make a coverage measurement and save that reports in this. So you can write that as coverage, a commit. It's not super strict. In some cases, you need like to fix your code a little bit, so there can be step away from this. And in red, yes, you're allowed to write like a method prototype as part of the red. So but I want you to really work with this. And this is awkward. This feels wrong. This goes against everything we've learned, more or less. So if you can, work in pairs with this part. There are individual examinations, and you might do good if you feel that you rely too much on the other person in your pair. You might be a good idea for you to do it a bit on your own also. It's not super strict in the way that one person should commit all the changes they do. You could have common commits and stuff like that. But in the end, it's a learning experience, the entire assignment. I'm not super interested in the project that you're creating and that it runs and that it actually is done. I'm more interested in seeing that you can follow this process, seeing that you've learned the JUnit and the the unit framework and the mocking framework and know about spies and stuff like that. And that is why assignment 1, part 2 has these questions. And so that discuss these questions with each other. If you don't find anyone to discuss these questions with, ask a question in Slack. Okay, get a question from Johan. What will the refactor commit include? So the refactor commit, for my example, I had 2 tests, and I really shouldn't. So my refactoring was removing 1 test. So I saved this file, and then I commit that as refactor. It can be changes in the system code. It can be other things during the refactor. So you're allowed to change both the test suite and the system code during the refactor phase, but you should not add functionality. You're just refactoring. You're just rewriting existing functionality so that the code quality becomes higher. And mostly that is about removing duplication. But it can be other things also. I mean, renaming things so that they're easier to read or things like that. So in the end, I would like to recommend a couple of books, and these are really the free books that I've read that I feel has given the most to me. And Clean Code is talking about how to write good quality code that is easy to read for someone else, another programmer, or yourself in the future. So it talks about that. It also introduces some things that are important for testing. Like if you have clean code, that should be testable, and sort of that book tells you about how to write this. Like, having less if statements in the same method, because it's easier to test. Okay, I got another question on this one. What if there is nothing to refactor at the refactoring step? Do we commit empty commits then? If there really is not anything to refactor, then look again. There are always things to fix. But yeah, the refactoring step could potentially, if you're so super awesome that you don't write any code quality mistakes, then yes, you could have an empty commit there, or you could skip that commit. It's not super strict as I write here. And perhaps you should read the Clean Code book in order to find out that you still have problems in your code. The test-driven development is part of the course literature, and I think that is a book you can read from start to finish almost. It is by Kent Beck. It's a bit religious. It's a bit hardcore TDD, of course. And it sort of explains all the steps. Yeah. The X-unit test patterns shows or tells you about a lot of different patterns. And some of you have heard about design patterns before. And these are test patterns. Well, things that you can test in different ways, and you can learn about different. And I find this book pretty good, but it's not what you should start with. So I think that you should start with this TDD book that I've written. Okay, I think that is enough for today. Hopefully you feel inspired to start up and work on assignment 1, part 2, after you've done assignment 1, part 1. Assignment 1, part 1 is due on Friday, right? It's November 16th, so make sure that you're all green there, and ask for help by our fantastic tutor instructors. Or write these questions on Slack and help each other a bit, but don't reveal the solutions, just help the other people to learn. And yeah, any more questions? Otherwise, thank you very much.